Hey guys, it's Stack Lessons here. Welcome to another practice exam. Today we've got 20 questions for you, covering RAG chunking strategies, AI gateway guardrails, and inference table behavior. A 10-second countdown after each one so you can pick your answer. Then the reveal. Pause whenever you need to. Good luck and enjoy. Okay, question 1. The wording narrows the answer. A generative AI engineer at Fairhaven Research is building a RAG system for a legal research assistant. Retrieved documents are ranked by the system, and the legal team wants the most authoritative sources to appear at the top of the result list. Relevance is graded on a multi-level scale. Highly relevant sources are far more valuable than partially relevant ones. The engineer needs a retrieval metric that captures both ranking position and the intensity of relevance. Which metric should they use? Select one. Review the answer choices on screen. The correct answer is option D. Graded relevance plus rank position, that's DCG. DCG at 10, discounted cumulative gain at 10, is the recommended metric when both ranking position and multi-level relevance intensity matter. It scores each retrieved document by its relevance grade divided by a logarithmic discount based on its position. So placing a highly relevant document at rank 1 contributes far more to the score than placing it at rank 8. This directly aligns with the legal team's requirement for authoritative sources to appear first. Recall, at K measures completeness, whether the system found all relevant documents, but does not consider their ordering or the degree of relevance. Precision at K measures how many retrieved results are relevant without distinguishing between a highly relevant and a marginally relevant result. Exact match applies a binary pass/fail signal and loses all graded relevance information. Okay, question 2. Match the answer to the situation. A generative AI engineer at Westport AI manages a shared foundation model API endpoint used by 3 internal teams: data science, product analytics, and customer success. The VP of engineering is concerned that a runaway automation script from any one team could exhaust the monthly token budget and disrupt service for the other teams before anyone is alerted. Which AI gateway feature directly prevents this scenario? Select one. Review the answer choices on screen. The correct answer is option A. Traffic tracking logs costs. It doesn't stop them. Rate limiting in AI gateway allows the platform to enforce maximum query per minute or token per minute thresholds at the endpoint level, the individual user level, or the group level. Applying limits per team or user group ensures that a runaway script from one team is throttled before it can consume the shared token budget, protecting availability and cost predictability for all other teams simultaneously. PII detection and redaction inspects payloads for personally identifiable information and replaces it with placeholder tokens. This is a data privacy control with no effect on request volume or cost exposure. Safety filtering blocks categories of harmful generated content such as hate speech or violence, which addresses content governance rather than resource consumption. Traffic tracking with cost attribution logs usage and assigns costs to teams after the fact for reporting purposes, but recording a cost after it is incurred does not stop a runaway script from generating unlimited requests before the budget is exhausted. Here we go. Question 3. Translate the story into requirements. A generative AI engineer at Prosware Legal is building a RAG application over a corpus of lengthy legal contracts. Initial testing shows that small 256 token chunks produce precise retrieval. The top K results are almost always relevant, but the LLM frequently generates incomplete answers because the retrieved chunks lack enough surrounding context to reason about cross-clause dependencies. Increasing chunk size to 1024 tokens improves answer completeness, but noticeably degrades retrieval precision. Which chunking strategy resolves this trade-off? Select one. Review the answer choices on screen. The correct answer is option B. Small chunk search. Large parent segments answer for you. Parent-child retrieval directly resolves the precision versus context trade-off by decoupling the search unit from the generation unit. Small child chunks of 512 tokens are indexed and searched, preserving retrieval precision. When a child chunk is retrieved, the system returns its larger parent segment of 2048 tokens to the LLM, giving the model the broader context needed to reason about cross-clause dependencies. Increasing K returns more small chunks, which adds noise and token overhead rather than providing coherent surrounding context for each retrieved passage. Semantic chunking produces variable-sized chunks that respect topic boundaries and improves coherence, but does not specifically address the need to supply large context to the LLM after precision-based retrieval. A 50% overlap ensures adjacent content is shared across chunks, but does not solve the problem of the LLM receiving insufficient context. It simply adds duplicate content per chunk rather than expanding the narrative window. Next up, question 4. Compare the distractors carefully. A generative AI engineer at Northdale Health is deploying an LLM-powered patient intake assistant fronted by AI Gateway. Regulatory requirements mandate that patient identifiers, including email addresses and social security numbers, must never reach the underlying model, and that any response containing violent or harmful content must be blocked before reaching the patient. Which two AI Gateway features should be enabled to satisfy both requirements? Select 2. Review the answer choices on screen. The correct answers are option B and option D. 5 options, 2 jobs, don't grab audit logs. PII detection and redaction actively intercepts each incoming request and replaces identified personal information, such as email addresses and social security numbers, with placeholders before the request is forwarded to the underlying model, directly satisfying the first regulatory requirement. Safety filtering inspects outgoing model responses and blocks any content matching harmful categories including violence before the response is delivered to the patient, directly satisfying the second requirement. Rate limiting controls throughput and cost exposure, but does not inspect or modify the content of individual requests or responses. Traffic tracking creates an audit log for post-hoc review, but does not prevent PII from being transmitted during an active interaction, and cannot block harmful responses in real time. Inference tables persist serving logs to a Delta table for monitoring and debugging purposes, but operate independently of AI Gateway guardrails and cannot enforce content policies during the live request-response cycle. Next up, question 5. Check whether it asks what or why. A generative AI engineer at Eastfield Systems deploys an LLM judge to automatically score response quality in a customer support chatbot. After running the judge on a set of responses that have already been rated by human experts, the engineer wants to quantify how closely the automated judge's ratings agree with the human ratings. Which metric should they use to measure this alignment? Select 1. Review the answer choices on screen. The correct answer is option B. Alignment beyond chance. That phrase belongs to kappa. Cohen's kappa is the standard metric for measuring inter-rater agreement, and is the metric MLflow tracks to assess how closely an LLM judge's scores align with human expert labels. Unlike raw accuracy, Cohen's kappa corrects for the level of agreement that would be expected by chance alone, providing a more honest measure of concordance between two independent raters. NDCG at K, recall at K, and precision at K are all retrieval quality metrics that evaluate how well a vector search component surfaces relevant documents. They measure retrieval performance against a ground truth document set, not the agreement between two scorers evaluating generated responses. Let's slow down here. The difference between an agreement metric and a retrieval metric is worth nailing down. Imagine a film magazine hires two critics and wants to know, do they agree on ratings? To check that, you'd compare their scores, not test the magazine's search engine. That's the trap here. The three distractor options all measure retrieval quality. They ask, did the search engine surface the right documents? Cohen's kappa does something different. It measures how much two raters agree, minus what pure chance would predict. Quick example, two raters agree 75% of the time, but chance alone gives you 50%. Kappa strips out that noise. Databricks uses this exact metric to certify that their LLM judge matches human experts. The exam rewards knowing the difference: search quality versus rater agreement. First 5 questions establish two core patterns. DCG and Cohen's kappa serve graded or comparative scoring, while parent-child retrieval is the repeating answer whenever search precision and generation context conflict. Next up, question 6 starts now. A generative AI engineer at Falcon Dynamics is auditing data lineage across the ML platform. The team wants to identify every registered model that consumes a specific feature table, providing customer risk scores, ahead of a planned schema change to that table. Which platform capability provides this traceability? Select one. Review the answer choices on screen. The correct answer is option B. Unity Catalog Lineage. It just knows, automatically. Feature governance and lineage in Unity Catalog automatically tracks the relationships between feature tables created with the Databricks feature engineering client and the models that consume those features via feature lookup. This lineage is captured without additional configuration and enables engineers to identify which registered models depend on a given feature table, making it straightforward to assess the downstream impact of a schema change before it is applied. MLflow experiment runs can include manually logged parameter tags, but the feature table name is not automatically captured as a structured lineage artifact that enables downstream impact tracing across all consumers. Inference tables capture request payloads and responses at serving time, logging the data values sent to the model rather than maintaining a registry of which feature tables contributed those values and their schema definitions. AI Search Index metadata describes the vector index and its source delta table, but has no knowledge of feature tables, risk score computations, or model consumption relationships. Now, question 7. This is a distractor check. A generative AI engineer at Blackmore Systems has enabled an inference table for a model serving endpoint and discovers that a subset of requests made during a high-traffic period are absent from the logged data, even though the endpoint was active and returning responses throughout. Which two conditions could explain why those requests were not captured in the inference table? Select 2. Review the answer choices on screen. The correct answers are option B and option D. 2 silent killers, size limits, and HTTP errors. Inference tables have 2 documented conditions under which requests may not be captured. First, payloads that exceed 10 MB in size are excluded from logging, so any large request or response crossing that threshold during peak traffic would be silently omitted from the table. Second, requests that return HTTP status codes 401, 403, 429, or 500 may not be logged, meaning rate-limited or server error responses during the traffic spike would also be absent. The client used to issue requests, whether the REST API or the Python SDK, has no effect on inference table capture, since logging is performed server-side and is independent of the request source. The number of AI search indexes attached to the endpoint is unrelated to inference table logging behavior. Provision throughput configuration does not affect whether inference tables capture requests. Logging operates the same way regardless of how model capacity is allocated. This one trips a lot of people. Let's nail down exactly when inference tables go silent. Picture a security camera that stops recording when things get crazy. That's kind of how inference table logging works. It captures most traffic, but two situations create silent gaps. First, any request or response over 10 MB is dropped. Imagine sending a 50-page document as the request body. That payload blows past the limit and never shows in the table. Second, error responses like HTTP 429, rate limit, and HTTP 500, server crash, are also skipped. Which client library sent the request? Doesn't matter. Logging is server-side. The trap: logs go quiet exactly when traffic is worst. Let us keep moving. Question 8. Match the answer to the situation. A generative AI engineer at Pinnacle Legal is building a RAG system over thousands of federal court opinions. During evaluation, small 256 token chunks retrieve highly precise passages, but the LLM frequently produces incomplete answers because each chunk lacks enough surrounding context. Increasing chunk size to 1024 tokens improves answer quality, but reduces retrieval precision, causing irrelevant sections to dominate the retrieved set. Which chunking strategy should the engineer adopt to resolve this trade-off? Select one. Review the answer choices on screen. The correct answer is option C. Retrieve precisely, then expand to the full section. Parent-child retrieval directly addresses the precision versus context trade-off. Small chunks, typically around 512 tokens, are indexed and searched to identify the most semantically relevant passages with high precision. When a small chunk is retrieved, the system returns its larger parent segment, typically around 2048 tokens, to the LLM instead, supplying the surrounding context needed for accurate generation. This preserves retrieval precision while ensuring the model receives enough material to reason from. Semantic chunking improves coherence within individual chunks, but does not solve the context gap, because the returned chunk is still bounded by the identified topic boundary. Fixed-size chunking with overlap is a reasonable baseline but cannot dynamically adjust the context returned based on what was retrieved. Raising the similarity threshold filters the results set more aggressively without adding context to the chunks that do pass the threshold. Let us keep moving. Question 9. Anchor on the exact workload. A generative AI engineer at Thornfield Manufacturing is building a RAG assistant that answers employee questions by drawing from two data sources: scanned maintenance PDF manuals and a live relational inventory database containing part numbers, stock counts, and reorder thresholds. Which two design decisions correctly handle each data source within the RAG pipeline? Select 2. Review the answer choices on screen. The correct answers are option A and option C. Embeddings for prose, SQL for structured numbers. Always. PDF manuals are unstructured text, making vector embedding in AI search the appropriate retrieval strategy. Semantic similarity search allows the pipeline to surface relevant manual passages even when the employee's phrasing differs from the document's exact wording. Inventory data is structured and relational, so querying it directly with SQL through a structured retrieval tool retrieves exact, current values. Stock counts and reorder thresholds require precision and do not benefit from semantic approximation. Converting inventory rows to prose chunks and embedding them in a vector index is inappropriate for structured data. It degrades numeric precision and pollutes the semantic index with content that does not embed meaningfully. Table summaries as vector chunks share the same problem, collapsing exact relational values into approximate prose. Feature serving exposes pre-computed feature values at low latency and is not designed as a query interface for answering ad hoc natural language questions about inventory. Let's pause here. Picking the right retrieval method for each data source is the core trap. Imagine building a helper bot for a factory. Two questions arrive. How do I fix bearing 47? And do we have 50 of this part in stock? Completely different retrieval paths. For the PDF manual, embed each passage as a vector. Run a semantic search to find relevant content, even if the employee's phrasing differs. For the inventory count, you need an exact number. Convert rows to prose and you lose precision instantly. Hit the live database directly with SQL. Feature serving stores pre-computed values for fast lookup, but it's not built to answer ad hoc inventory questions. The exam tests whether you match the retrieval method to the data shape. Time for another one. Question 10. Do not rush the wording. A generative AI engineer at Litware Financial is deploying a customer-facing loan qualification assistant through Databricks Model Serving. The assistant is expected to handle approximately 50,000 queries per day with peak traffic during business hours, and the team requires consistent performance and predictable costs at scale. Which pricing model should they select for the model serving endpoint? Select one. Review the answer choices on screen. The correct answer is option C. Pay per token is not a production pricing strategy. Provisioned throughput is the recommended pricing model for all production workloads, particularly at high query volumes. It allocates dedicated compute capacity, guarantees consistent throughput, and provides predictable billing at scale. Pay per token is appropriate for development and early-stage testing when query volumes are low and unpredictable, not for production scenarios requiring guaranteed throughput. Databricks documentation explicitly states that pay per token is not suited for high-throughput production use. Routing through AI gateway to external models introduces additional latency and external billing without solving the capacity consistency problem, and still incurs per query charges from the external provider. Middle batch confirmed Unity Catalog lineage wins every upstream tracing question, that inference tables have 2 silent exclusion conditions worth memorizing, and that pay per token is explicitly not suited for production scale. Time for another one. Here's question 11. A generative AI engineer at a video streaming platform is building a content moderation system that must analyze both thumbnail images and short video clips to detect policy violations. The system must process both input types in a single model call and generate a structured report. The platform uses the Databricks Foundation Model API. Which model should the engineer select? Select one. Review the answer choices on screen. The correct answer is option D. 4 modalities, 1 call. Only Gemini handles video. Gemini 2.5 Flash is the correct choice because Gemini family models available through the Foundation Model API natively support all 4 input modalities: text, image, video, and audio. This native video support is the decisive differentiator that allows a single model call to process both thumbnail images and video clips without any additional pre-processing pipeline. Claude Sonnet 4.6 supports text and image inputs within the Foundation Model API, but does not support video as an input modality, making it incapable of natively ingesting video clips for policy analysis. Llama 4 Maverick similarly supports text and image inputs only, and cannot process video content without a separate frame extraction step that reroutes the workload outside the model's native capabilities. BGE Large is an embedding model that produces vector representations for retrieval and similarity search. It cannot interpret visual or video content, cannot detect policy violations, and cannot generate structured text output of any kind. Time for another one. This is question 12. Quick check. A generative AI engineer at Tailspin Media is building a content moderation pipeline that processes user-uploaded posts. Each post can contain a text caption, a thumbnail image, or a short video clip, and the system must classify whether any content violates community guidelines. The engineer wants a single Foundation Model API call that natively handles all 3 modalities without pre-processing video into separate frames. Which model should they use? Select one. Review the answer choices on screen. The correct answer is option D. You've seen this shape. Video native means Gemini. Gemini 2.5 Flash is the correct choice because Gemini family models available through the Foundation Model API natively support all 4 input modalities: text, image, video, and audio. This native video support is the decisive differentiator that allows a single model call to process both thumbnail images and video clips without any additional pre-processing pipeline. Claude Sonnet 4.6 supports text and image inputs within the Foundation Model API, but does not support video as an input modality, making it incapable of natively ingesting video clips for policy analysis. Llama 4 Maverick similarly supports text and image inputs only, and cannot process video content without a separate frame extraction step that reroutes the workload outside the model's native capabilities. BGE Large is an embedding model that produces vector representations for retrieval and similarity search. It cannot interpret visual or video content, cannot detect policy violations, and cannot generate structured text output of any kind. Ready. Now for question 13. A generative AI engineer is assembling a RAG pipeline for a legal research assistant. The retriever has returned 3 relevant case summaries from AI search. Before sending anything to the LLM, the engineer needs to combine those retrieved passages with the user's original question and a system instruction describing the assistant's role and constraints. Which component of the RAG pipeline is responsible for this combination step? Select one. Review the answer choices on screen. The correct answer is option D. Augmentation step. Who assembles the final LLM input? The prompt template is the RAG pipeline component responsible for the augmentation step. It takes the retrieved documents, the user's question, and any system instructions and formats them into a single structured prompt that the LLM can consume. This is the core of the augmentation phase in Retrieve, Augment, Generate. The embedding model produces vector representations of text to enable similarity search. It does not combine text for generation. The retriever's role ends once it has returned relevant documents from the index. It does not restructure or append system instructions. The feature store endpoint provides real-time features such as live scores or current user state, which are a supplementary data source and not the component that assembles the full LLM input. Let us switch gears. Question 14. Look for the constraint that matters. A generative AI engineer is building a contract summarization service for a law firm. The contracts are lengthy, frequently exceeding 100,000 tokens each. The engineer needs to select a Foundation Model API model capable of ingesting an entire contract in a single inference call without truncation. Which factor should drive the selection decision? Select one. Review the answer choices on screen. The correct answer is option C. The binding constraint is context window, not model family. When input documents exceed 100,000 tokens, the model's context window is the binding constraint. Only models with context windows of 128,000 tokens or more can ingest the full document in a single API call without truncation. Within the Databricks Foundation Model API, Llama 3.370b supports a 128,000 token context window and Gemini 3.1 Pro supports up to 1 million tokens, both sufficient for the described contracts. Embedding dimension is a property of embedding models used for vector retrieval and does not describe how much text a generative model can process in a single forward pass. Code-specialized models such as Code Llama 34b are optimized for programming language patterns and would not provide the legal language comprehension that contract summarization requires. Chunking and summarizing segments separately works around context limits, but loses cross-document coherence, A contract may have clauses that only make sense in relation to other sections and requires additional merge logic to produce a cohesive summary. Let us switch gears. Let's read question 15. A data engineering team has built a recommendation model that consumes features derived from user activity tables and product inventory tables stored in Unity Catalog. After the model is deployed to a serving endpoint, the data governance team asks which upstream tables contribute to the features used by the live endpoint. Which capability provides this answer automatically without requiring the team to maintain manual documentation? Select one. Review the answer choices on screen. The correct answer is option C. MLflow tags versus Unity Catalog. One requires discipline. Unity Catalog automatically tracks data lineage across the full pipeline, from source tables, through feature store transformations and materialization, to the serving endpoint, and surfaces this as a queryable lineage graph. The governance team can navigate this graph natively without any manual documentation effort, and the lineage remains accurate as the pipeline evolves. MLflow experiment tags require engineers to manually record table names and quickly become stale or incomplete when pipelines change. Inference tables capture the inputs and outputs of live inference requests, but have no visibility into where those input features originated upstream in the data pipeline. Custom audit log analysis requires significant engineering effort to reconstruct lineage and must be repeated each time the governance team needs to answer the question. Questions 11 through 15 showed Gemini 2.5 Flash as the only foundation model API choice with native video support, and confirmed that prompt templates own the augmentation assembly step inside a RAG pipeline. Keep your focus here. Question 16. Do not rush the wording. A generative AI engineer at Fairfield AI deployed a customer support chatbot with an inference table enabled to capture all requests and responses. 2 months after deployment, the DBA team added a session_context column to the inference table to store additional metadata for downstream analysis. The following morning, the engineering team discovers that no new records have been written to the table since the column was added. What is the most likely cause? Select one. Review the answer choices on screen. The correct answer is option B. Schema change after enable. What stops logging entirely? Inference tables stop logging if the table schema is changed after the inference table has been enabled. Adding the session_context column altered the schema, causing the inference table to cease writing new records entirely. Modifying the schema, changing the table name, or deleting the table are all conditions that permanently halt logging. The concurrent request limit affects request handling throughput, but does not stop inference table logging. The sampling_fraction parameter does not reset automatically. It retains the value configured at setup unless explicitly updated. The 10 MB payload limit prevents individual oversized payloads from being logged, but would not halt logging for the entire table's traffic. Let's slow down here. Adding a column to an inference table is way more dangerous than it sounds. Imagine your customer support chatbot has been logging every conversation for 2 months. Perfectly. Then the database admin team adds a column called session_context to the inference table. Sounds harmless, right? Wrong. Databricks inference tables have one hard rule. The schema must never change after the table is enabled. The moment that column is added, the endpoint detects a mismatch. It flips to a failed state and stops writing entirely, not one record. The 128 concurrent request limit and the 10 MB payload cap are real, but neither halts all logging. And sampling_fraction doesn't auto-reset after 60 days. The trap here is assuming a schema change is just additive. For inference tables, it's a hard stop. All right. Question 17. Keep the constraints in view. A generative AI engineer at Ironwood Medical is building a clinical research assistant. Physicians query a large database of medical case reports to find relevant precedents. Small chunks improve retrieval precision by narrowing results to the most relevant paragraph, but the model's generated answers lack sufficient clinical context because the surrounding treatment narrative is truncated. Which chunking strategy best resolves both retrieval precision and contextual completeness simultaneously? Select one. Review the answer choices on screen. The correct answer is option D. Parent-child retrieval. Still the answer for this scenario. Parent-child retrieval directly resolves the tension between search precision and context completeness. Small 512 token chunks are embedded and searched to pinpoint the most relevant passage in a case report. Then the system retrieves the larger 2048 token parent segment containing the matching chunk, supplying the LLM with the full surrounding clinical narrative for generation. Fixed size 1024 token chunks with no overlap broaden context but reduce retrieval precision because the indexed unit is large and semantically diffuse. Semantic chunking improves boundary quality by grouping topically coherent sentences, but does not solve the context problem. The indexed chunk is still the unit returned at retrieval time, with no mechanism to expand to surrounding material. Fixed size 256 token chunks with overlap maximize precision at the cost of even less context per retrieved unit, exacerbating the truncation problem. Alright, question 18. Do not stop at the first match. A generative AI engineer at an enterprise software company manages a shared AI gateway endpoint used by 7 internal product teams. 2 concerns have been raised. First, that a single team running batch experiments could consume all capacity and degrade response times for the other 6 teams. Second, that total API spending must remain predictable and within budget. Which 2 AI gateway features should the engineer configure to address both concerns? Select 2. Review the answer choices on screen. The correct answers are option D and option E. 2 rate limit levels, 2 separate problems to solve. Rate limiting at the user level prevents any single user or service account from monopolizing endpoint capacity, directly addressing the concern that one team's batch experiments could degrade throughput for the remaining teams. Rate limiting at the endpoint level enforces an overall cap on all requests flowing through the gateway, which protects the total cost budget by preventing runaway API spending regardless of which team triggers it. PII detection and safety filtering are content-level guardrails that address data privacy and content quality concerns. They do not limit consumption volume or protect against capacity exhaustion or budget overruns. Traffic tracking logs and attributes usage for visibility and reporting purposes, but does not enforce any limit that would prevent overconsumption. Let's break down the wording here. This question hides 2 problems that need 2 separate fixes. Imagine 7 teams sharing one elevator. One team books it all afternoon. Everyone else is stuck. That's this question. But for API capacity and budget, which 2 means 1 answer per concern? Fairness and cost. Address both concerns is the trap. Options A and B are real AI gateway features, but they control content, not consumption. Option C, traffic tracking, tells you who spent what after the fact. It doesn't stop anyone. User-level rate limiting caps each caller. Even if Team A runs 10,000 batch jobs, Teams B through G keep their share. Endpoint-level rate limiting sets the overall ceiling. That ceiling is your budget ceiling. The question rewards distinguishing enforce from observe. Okay, careful on question 19. This one has a trap. A generative AI engineer is preparing a foundation model API endpoint for a production legal summarization service. Load testing shows a consistent baseline of 3,000 tokens per second, with spikes reaching 12,000 tokens per second during business hours. The team wants to eliminate cold start latency during business hours while auto-scaling to handle traffic peaks without over-provisioning at all times. Which configuration approach should the engineer use? Select one. Review the answer choices on screen. The correct answer is option D. Minute sets the floor. Max sets the ceiling. Setting minimum provisioned throughput to the consistent baseline of 3,000 tokens per second ensures warm compute is always available, eliminating cold start delays. Setting the maximum to 12,000 tokens per second allows the endpoint to auto-scale up during traffic spikes without holding unnecessary capacity during quieter periods. Pay-per-token mode is recommended for development and low-volume exploration, but cannot guarantee pre-warmed capacity for production workloads with consistent baseline demand. Setting the minimum to the full peak load of 12,000 tokens per second holds maximum capacity at all times, which wastes budget during off-peak periods. Switching between endpoint types via a scheduled job adds operational complexity and reintroduces cold start risk during every transition window. Okay, question 20. Quick check. A generative AI engineer at Meridian Health is deploying an LLM-powered patient support chatbot. Regulatory requirements prohibit SSNs, phone numbers, and email addresses from appearing in any response sent to end users. The team wants to enforce this rule at the gateway layer without modifying application code. Which AI gateway feature should they configure? Select one. Review the answer choices on screen. The correct answer is option D. Safety filters block content. PII detection scrubs identifiers. PII detection and redaction is the AI gateway feature that identifies personally identifiable information, including SSNs, phone numbers, and email addresses within requests and responses, then automatically replaces them with placeholders before the content is forwarded. This enforces the compliance requirement at the infrastructure layer without any changes to application code. Safety filters are designed to block hate speech, insults, sexual content, and violence categories. They do not target structured identifiers like SSNs or phone numbers. Rate limiting controls how frequently a user or group can send requests and has no capability to inspect or modify the content of those requests. Traffic splitting distributes requests across different models or endpoints based on routing rules, but does not inspect or sanitize payload content. 3 takeaways from this session. First, parent-child retrieval decouples the search unit from the context unit, resolving precision completeness tension at index design time second. Rate limiting controls throughput. PII detection scrubs identifiers. AI gateway multi-selects hinge on knowing which guardrail does what. Third, inference table logging silently halts on schema modification and excludes payloads over 10 MB or HTTP 4xx/5xx responses. Precision versus context, guardrails versus budget, lineage versus manual docs. These trade-offs define real production systems. Understand the mechanics behind each, and the exam scenarios stop being puzzles and start being patterns you already recognize.